So in today's video, we are going to be talking about reaction rate and energy and how these concepts relate to our understanding of chemical reactions, what we've been talking about so far. And so when we're talking about reaction rate and energy, these concepts are really going to be centered around this idea of kinetic molecular theory, or KMT. And remember, we did discuss KMT earlier in the year. But it's here again to help us kind of remember. So KMT states that molecules are going to be always in motion, so they're constantly moving. And the energy of those molecules is dependent on the temperature. So the higher the temperature, the more energy the molecules have. And the way that this kind of relates to the idea of reaction rate is that in order for a reaction to even happen, two things have to be satisfied. So the first thing is that the molecules in themselves have to have the correct orientation. They have to be facing in a correct direction. And usually what that is it's going to be like a head-on collision. If they're not hitting each other in the correct orientation, they're not going to react. The second criteria is that they have to have enough energy. So obviously, if you have a higher temperature, the likelihood of those molecules having enough energy to cause a reaction is going to be greater. So again, looking at that first criteria, particles have to collide with one another in the correct orientation. Generally, this is a head-on collision. And they have to collide with the correct orientation so that the bond breaking between molecules and the bond forming between molecules can happen. If they're not, if they're just bouncing around and they're not actually having head-on collisions, we have what we call unsuccessful collisions versus those head-on collisions, which are generally going to be our successful collisions. So they have to collide with the correct orientation. That's the key part here. So we saw at the start of the video that the first criteria is that molecules have to collide with each other in the correct orientation. The second criteria is that they have to have a certain amount of energy during a collision in order to react. So if they have a very low energy, the chances of a chemical reaction happening are not super great or super high. And that energy that particles need to have in order for a collision to happen is what we call the activation energy, or the EA is how you abbreviate it. The EA, or the activation energy, depends on the type of reactants, and having a lower activation energy actually indicates a faster reaction rate because the particles being able to reach that activation energy is going to be a lot easier. What we're looking at down here is called a reaction pathway. So a reaction pathway is simply going to show our particle orientation and the energy transfer within a reaction. So the cool thing about this, and hopefully this looks a little bit familiar to you from biology when you were looking at enzymes and how enzymes help lower activation energy to speed up chemical reactions in the body. So here we have our reactants on the left-hand side. We have our products on the right-hand side. The amount of energy that the reactants need to have in order to react, it's called that activation energy. And then we have this difference here, which is what we're going to call delta H. And we're going to come back to this idea of delta H and what that means in a little bit. So there are four things that affect reaction rate. The first one is the idea of surface area. So if you have a higher surface area, it allows for more collisions to happen, and the more collisions that happen at a faster rate generally means that we're going to have more successful collisions. So you can increase surface area by simply decreasing the particle size or dissolving something in water. So think about that as we see it here in the video, or in the image at the bottom. So we see a whole piece of calcium chloride versus many little pieces of calcium chloride. So between steps 1 and 2, between those two numbers, we've increased the surface area by breaking down that big chunk of calcium chloride into many smaller pieces. So why would small particles increase rate? It's because the more surface area present leads to more collisions. And the more collisions we have, again, the more likely it is for us to have a successful collision. So the next factor that affects reaction rate is the idea of concentration. So remember, concentration is the amount of particles in a given area. So having a higher concentration also equals a faster rate. So high concentration of particles, faster rate. And the reason for this is that the higher the concentration, the more likely the particles are to bump into one another. And again, the more collisions they're having, the more likely we are to have a successful collision. So I want you to think back to the beginning of the video where we were talking about collisions, and I want you to answer the question down below. Does every collision result in a reaction? And the answer to this is no. Remember, only collisions with the correct orientation of particles is going to actually result in a reaction. So our third factor that's going to affect reaction rate is going to be that idea of temperature. And remember here we're kind of thinking about that concept of KMT. So remember, higher temperature equals a faster rate simply because higher temperatures also mean higher kinetic energy. And the more energy the particles have, the more likely it is that they'll be able to overcome their activation energy and actually result in a reaction. So that's going to be the answer to number 2, or I'm sorry, to number 1, this first bullet here. So why would increasing temperature increase the kinetic energy? Increasing the temperature increases the movement of the molecules, or the movement of the particles. And if they're moving more, they're going to have more kinetic energy. And then looking at number 2, the second bullet here, so why would higher kinetic energy increase in reaction rate? Particles are more likely to have the energy they need to overcome that activation energy. All right, so let's go ahead and move on and look at our fourth factor that affects reaction rate. So the last factor that affects reaction rate, and one that you should be familiar with from biology, is this idea of a catalyst. So a catalyst is simply anything that increases the rate of a reaction without being consumed by the reaction. So if it's not being consumed by the reaction, characteristic of catalysts is that they can be reused. And the way that catalysts increase the rate of a reaction is they lower that activation energy. So the lower the activation energy, the more likely the particles are to be able to obtain that energy, and the quicker that the reaction can happen. So far we've covered a lot about reaction rate. Now we're going to switch gears a little bit and focus more on the energy part. So the key thing to remember about energy is that during a chemical reaction, energy is always going to be conserved. It can't be created or destroyed during a reaction, but it is going to probably change form. It usually changes form. So if you think about this, like when we're heating a reaction, that heat energy, the energy coming from the heat source, simply gets converted into chemical energy that we use to break bonds. So again, we're not creating energy or destroying it, we're simply changing the form of that energy. So when we think about energy, we can have what we call an exothermic reaction or an endothermic reaction. And we're going to start here with thinking about energy and exothermic reactions. So if the reaction itself heats up, then energy is going to be released. So the reaction ends up releasing energy to the surroundings. And remember, here energy and heat are going to be pretty synonymous. So that's when we're thinking about things getting really hot, explosions may be happening, things like that. And because the reaction is releasing the energy to the surroundings, it means that the products are going to have less energy in the reactants because that energy that the reactants had is being released to the surroundings. So we can take a look at an example here of thermite. So here we're looking at iron 3 oxide reacting with aluminum. And this is an extremely exothermic reaction, and it's a single replacement reaction. And because it's exothermic, we're losing heat to the surroundings. So when we look at the reaction pathway, remember that's what this is called here. So these are what we call reaction pathways or reaction diagrams. So when we look at this reaction pathway, we see that the reactants start with a certain amount of energy. We have to overcome that EA. Remember, EA is the activation energy. And once they overcome that, then the reaction is actually happening from this peak down to where we see the products being produced. And that delta H is going to be change in energy. So we're looking at the change in energy between the products and the reactants. So here we see in our exothermic reaction, the products are going to have less energy than the reactants because some of that energy is being lost to the surroundings. So the opposite of an exothermic reaction is going to be an endothermic reaction. And you can think about endothermic as heat. Remember, thermic meaning heat, heat entering. So endo, we're thinking about heat entering. So what is that heat entering? Well, the heat is entering the reaction. So in endothermic reactions, one of the things you're going to be looking for is when the reaction cools down. So when it feels physically cool to the touch, energy is actually being gained into the chemical reaction. That reaction is pulling energy in from the surroundings. And because it's pulling in that energy from the surroundings, it's creating the feeling of cool touch, cool environment to the touch, because that heat is being drawn into the chemical reaction itself. And so since the heat or the energy is being pulled into the chemical reactions, the reactants are actually going to end up having less energy than the products. So again, remember the amount of energy it takes for the reactants to actually start the reaction is this idea of activation energy. And then once the reaction's actually going, this delta H is going to be change in energy, which remember delta H is going to equal energy of the products minus the energy of the reactants. So if we think about our delta H values here, because the products are going to have more energy than the reactants, in an endothermic reaction, our delta H is going to be a positive value, whereas in an exothermic reaction, our delta H is going to be a negative value. All right, so I'm going to get you started on number 1 here. So here we have 2 different reaction pathways, and we need to determine the delta H and the activation energy for both of them, and then we need to determine whether the reaction is exothermic or endothermic. So thinking about our characteristics of a reaction pathway, remember we're always going to start with the reactants on the left-hand side and the products on the right-hand side. What is it called? What is the term we use to talk about the energy required by the reactants, or the energy needed by the reactants in order for the reaction to occur? So hopefully you remember that this is going to be our activation energy. And so in order for us to calculate this, we have to do 100 kilojoules minus 40 kilojoules. So our activation energy is going to be 60 kilojoules. And then remember, delta H is going to be the change in energy. So here our products are going to have 20 kilojoules of energy, and the reactant started with 40 kilojoules of energy, which means that we're going to have a delta H value of negative 20. So since we have a negative delta H value, we know that this is going to be an exothermic reaction. And remember, that holds true with the idea that our products are going to have less energy than our reactants because some of the energy that the reactants had is being lost to the surroundings. So the products end up having less energy overall. So now I want you to take a look at the bottom reaction pathway, and I want you to calculate the activation energy, the change in energy, and tell me whether or not you think that reaction is exothermic or endothermic.